So hello there, my name is Tamnai Bakshi, and today we're going to be talking about why exactly BERT performs better on downstream tasks if it's trained twice in the pre-training stage. Once on a very large corpus of text data, and then once on domain-specific text data. Now, one thing I do want to say before we actually start today's tutorial is that if you do enjoy this kind of content and you want to see me make more of it, please do make sure to subscribe to the channel, as it really does help out a lot, and turn on notifications. That way you're actually notified when I release videos like this one. Apart from that, if you do enjoy this video, please do also make sure to hit the like button, and if you have any questions, feel free to leave them down in the comments below. Now, personally, this is something that I'm really interested in because I've started to see this shift from training architectures and training regimes really for neural networks that are mostly, hey, let's train a network on our task. And then we saw this evolution towards, well, maybe we can fine-tune some neural networks and get them to do other things. Like, for example, if we train a network on ImageNet, then maybe we can, specialize it to cats and dogs or something of that sort. And now we're seeing this full-on sort of transfer learning approach where we're trying to say how much insight can we extract from just data, right? From just as much data as we can get. And then how can we go ahead and specialize these neural networks to work really, really well on other kinds of sort of domain-specific data. Now, personally, I find this really interesting, and sort of the field that's been leading this evolution, I believe, is the field of natural language processing. Now, depending on how many of my videos you've watched before, you probably know that A, I'm really passionate about machine learning technology, and that B, natural language processing and natural language understanding in specific is my favorite sort of subfield within machine learning technology. Reasons for that are, many different reasons actually, but really it's because natural language is so complex. Not only do we need to be able to sort of encode within machines generic and sort of imaginative thoughts that we have as humans, but we also somehow have to make it work across domains, right? No matter what exactly that language is about. And that can be really difficult, right? It's like, for example, BERT was trained on just hundreds of gigabytes of just text from the internet. And that enables BERT to be a really good natural language understanding engine, which we can then fine-tune on what are known as downstream tasks, things like question answering or natural language classification or regression or things like this. But then, in between, there's a sort of, I would say, rarer step that not as many people do, but can be incredibly helpful. And that is the same sort of pre-training stage, but once again for your own domain-specific data. So, before we get into that, let's take a little bit of a step back. What is BERT? Now, if you're watching this video, I assume you already know a little bit about the BERT network, but just as a quick recap, BERT is a natural language understanding or a transformer built with the goal of being able to understand natural language. This was developed by Google a couple months ago, and it's really brought a revolution into the world of natural language processing technology. Right now, pretty much every NLU solution out there is powered in some way by this BERT neural network or its derivatives. Now, the thing about BERT is that it's trained with a really, really interesting scheme. Well, there are technically two of them, but the main one is called masked language modeling. Now, you may recognize the term language modeling from neural networks that can generate language. So, for example, being able to take a word and then predict the next word, and then take those two and then predict the third word, and so on and so forth until you reach the end of a sequence. Well, masked language modeling is similar, but except instead of going from left to right and continuously generating more words, what's fed into BERT is a whole sentence with a certain number of tokens or words just randomly removed. And then what they actually train BERT to do is fill in the blanks. So BERT is going to learn the sort of internal representation of natural language just based off of filling the blanks. That is incredible. Who would have thought that we can train neural networks to not only understand natural language, but even structure it internally mathematically similarly to how we as humans do, just by training them to fill in the blanks. I think that's really interesting. It's kind of like how we teach kids to read and write. Now, BERT is also trained on what's known as the next sentence prediction task, which enables it to take two sentences and basically predict, is sentence B what comes immediately after sentence A, or is it just some completely random sentence? However, the researchers over at Facebook sort of determined that wasn't really necessary. It didn't really help out the training process at all. And so with their Roberta network, they kind of just didn't do the next sentence prediction. And so whether or not that's needed is a whole sort of debate. It sort of helps out some downstream tasks, but the vast majority of them it doesn't. And there are other kinds of training objectives that are better. But regardless, what we're focusing on today is masked language modeling. Now, after the masked language modeling objective, usually what pretty much anyone would do is they would go to the Google website or GitHub repo for BERT. They would download the BERT model, they would use their own data, and they would just fine-tune BERT and its generic natural language understanding engine on their data. And that's what I've been doing, that's what everyone's been doing. But if you'd like to go the extra mile, if you have, for example, lots of unlabeled text data that is specific to your domain, but only a little bit of labeled data, then you can do what's known as a second step of pre-training. You can take the pre-trained BERT and run masked language modeling once more on your own data before you run your downstream task. Now, the reason for this is not because you want BERT to play fill in the blanks with you, but because what's going to happen is BERT is going to adjust its data distribution, or the way that it expects the data to be distributed as input, to match your domain-specific language. Now, I've been working on a couple of different projects that are based on this foundation of very powerful NLP. One of them is in the field of music. It's something that I haven't really talked about just yet, but one of the components for this project requires utilizing BERT. Now, as you can imagine, it's really difficult to get access to large amounts of labeled data when I'm working with this sort of field. And it's not very generic language either. It has a very specific theme to it. Sometimes it ignores grammatical rules and punctuation and spacing, and therefore I need a very custom version of BERT to work here. So what I've gone ahead and done is I have actually put together a real example of how that secondary stage of pre-training helps BERT, and we'll talk about why exactly this all works as we take a look at the code as well. So let's quickly dive into this. Now, to start off, I'm going to tell you what I did. As I said, BERT's already been trained with masked language modeling. What I've done is I've gone ahead and I have downloaded a couple 10,000 song lyrics from the Genius website. Now, what I've done is I've taken each set of lyrics and I've split them by the individual line. So just line by line, not section by section, just line by line. Then what I did is I put together a little script that would automatically go through each line and make two versions for each. One where 15% of the tokens are just masked out randomly and removed, and the other one's just the original. Then I retrained BERT to do that fill-in-the-blank task. And before we take a look at why exactly this was so useful for me, let's just take a look at some of the outputs from the network to begin with. Now we're going to start off with what I think is a really interesting example. It's an example where the network, it's competent, but you can see that the second step of pre-training didn't really help out that much. So I'm going to go ahead and take this line over here from Genius, and I'm going to feed it into both neural networks. You can see both pieces of output on screen right now. On the left, you can see the top 10 predictions from the network that I fine-tuned to be really good at filling the blanks for lyrics specifically. On the right, you can see the output from the network that wasn't fine-tuned. This was just directly downloaded from the Hugging Face repository for neural networks, or transformers to be specific. As you can see, looking, which is indeed the gold standard label, is the top prediction for both models. To give you a bit more context, this is the base model for BERT. I'm not really using the large model here. So looking, which is the gold standard label, is indeed the top prediction. Now, this is a bit more subjective, but if you were to go down in the top 2, 3, etc., you might notice that the network that was fine-tuned for music lyrics comes up with words that would still be more plausible to be part of a song rather than the non-fine-tuned BERT, which is just trying to fill out the sentence as if it's just somewhere random on the internet. But then again, that is a bit more subjective, so I'm not going to try to do an objective analysis of that right now. Instead, I want to move on. So we've seen an example where both networks achieve pretty much the same outcome. And I'm showing you this because I don't necessarily want to cherry pick the results that I show you here. Now I want to show you an example where both completely fail. All right? And it's not because the neural networks aren't competent, once again, it's because the context is just too varied. All right, so what I've done is I've gone ahead and taken this specific line from this song, all right, and I masked out the word lining. And I fed this into my neural network as well as the original BERT network. And both of them had absolutely terrible output. Now, again, you might say that the one that's fine-tuned has slightly better output, as in, it would make a little bit more sense for picking to be here instead of brought, which is the second top prediction, respectively, for both models. But then the word lining isn't there at all. However, I will say that the fine-tuned model did get a lot closer. As you can see, down at rank number 7, we do have the word lined, which is close to lining. Again, it doesn't really mean the same thing in context here, but you can argue that the fine-tuned network was in a sort of closer ballpark or radius versus the model that wasn't fine-tuned at all. So you've currently seen an example where both networks are pretty much the same, both networks pretty much fail. So you're probably saying, well, what's the value here? Why would I go through all that extra effort to actually do the extra pre-training step? Now remember, you haven't seen actual downstream performance just yet, but I will show that to you in just a moment. Now, I want to show you some truly mind-boggling examples that I think really prove why this is such an important step. Let's take a look at them on my computer right now. Now, as you can see, what I've gone ahead and done is I've gone ahead and taken this line from this song. Now, as you can tell, in sort of general context on the internet, you more than likely wouldn't see this kind of line. If you were just browsing Reddit or if you were just browsing Facebook or Twitter, you probably wouldn't see this line anywhere. But in a song, you wouldn't bat an eye at it. It's just there. Of course it would be. It's music. So I'm going to go ahead and feed this into both my fine-tuned and the original network, and I'm going to mask out the word sheets. Now, as you can see, the fine-tuned network just blows the original one out of the water. Now, the gold standard label is the #1 prediction for the fine-tuned model, and the original doesn't even get the gold standard in the top 10. I think that is absolutely incredible. Now, you can see that BERT is trying its best. It's like, where could a stain be? Well, maybe there would be a stain on the floor, maybe the walls, maybe a counter or a carpet. But it's unable to get the word sheets because, well, that's a very, song domain specific context extension. But what I think is an even more sort of extraordinary application of this is when we move the mask to the very beginning of the sentence. Now, it's going to be the exact same sentence. We're going to remove the mask from the word sheet, so we're going to put that back there. But then I'm actually going to go ahead and have the models predict on the first word masked instead. And as you can see, once again, the fine-tuned model just absolutely shreds the original model's performance. The original model isn't even close in what it's trying to fill, whereas the fine-tuned model, instantly, right there, it's got the word lipstick, first prediction, it's got. Now, what I personally find so incredible about this is think about it. The word lipstick stains and the word sheets didn't appear in the same context that this neural network was trained on at all. It was actually taking these different pieces of data that referred to different concepts in different contexts, and it's able to sort of generalize them in its internal structure in order to make it so when we refer to something as a brand new imaginative concept, just like that, it's able to predict what the masked word should be. Now, while the fill-in-the-blank performance may be amazing, you're probably wondering, well, does it really help you in a downstream task? And well, yes it does. Because think about it. If you're able to better predict what words should be, that doesn't mean you have a better word predictor. That means you have a better embedder. You have a better every single layer in BERT before the last one that is working towards embedding your entire sequence into a space in which it makes sense in your domain. And the networks that are responsible for taking the output of those embeddings and actually doing something with them in a downstream task will then have better more contextualized embeddings to use. I mean, think about why BERT is so powerful in the first place. It's massive contextualization. And with this technology, we're getting further and further contextualization. Now, what's absolutely amazing about this is just how simple it is to fine-tune the networks themselves. I mean, take a look at this. In order to add this pre-training stage, there were really just two main steps I had to do. First of all, I put together the following data Python file. What this does is it goes ahead and takes, of course, the Hugging Face libraries, the Transformers library specifically from Hugging Face, and it goes ahead and imports the simple base BERT model as well as its tokenizer. I define a couple of functions, like for example, a function that's responsible for tokenizing input, a function that's responsible for actually masking out some of those values at random, another function that's responsible for sorting and batching a bunch of different inputs into batches where BERT can actually go ahead and use them efficiently on the GPU. And then all I gotta do is go ahead and save those outputs to my disk. And then what I do is I've got a little bit of a training script here. And what this training script does is it uses the power of the library known as PyTorch Lightning in order to do what it is that I'm doing, which is training this BERT model in a way easier way than I could ever implement from scratch using PyTorch and Hugging Face library. And specifically what I mean by that is if we go to the end of the code, I'm using what's known as a PyTorch Lightning trainer module in order to automatically just say, you know what, I want to use distributed data parallel backend, I want to run 4 epochs, and I want to run on 4 GPUs on this machine. Just like that, PyTorch Lightning is handling it, and I've got my model training on 4 GPUs, and it's using distributed data parallel, which is way more difficult to implement than the regular data parallel in PyTorch, but it's so much more efficient, so it makes it worth it, and PyTorch Lightning makes it that easy for me. Now, if you take a look at the actual code that goes behind training, the basic concepts are pretty simple. Of course, I've got the dataset module, which is basically just over here to enable me to load in my data, which is essentially just loading in a pickle that I had already created from my data processing script, because of course every time I run the training I don't want to reprocess my data because that takes some time. And then I've got this little PyTorch Lightning module over here that's responsible for opening up a pre-trained BERT model from Hugging Face, going ahead and feeding my data into it along with the mask that prevents me from actually attending to padding tokens. And then from there, I'm just going ahead and running a training step, which is feeding data into the network, getting the loss based off of the masked language modeling objective, and then returning that loss over to PyTorch Lightning where it can determine what exactly my new neural network weights need to be. And it does that using the atom optimizer that I define over here. So the basic code for fine-tuning is incredibly simple. This is already on GitHub, and there will be a link to it down in the description. Unfortunately, I cannot provide you with a data set for this, but if you do have your own data set, you can easily repurpose this code and make it work for your own data and for your own tasks. And of course, just to show you once more, you're probably finally wondering, well, I clicked on the video to figure out what the performance difference is, and here it is. The performance difference for me here is usually a difference in loss from about 0.52 for my usual downstream tasks to 0.49 when I'm training on with a fine-tuned pre-training objective. Now you're probably wondering, what do those numbers mean? Well, unfortunately, I can't tell you what the task is that I'm training on because, once again, this is an objective that I can't share with you just yet. But the idea is that I'm using, in general, a triplet loss function, customized version nonetheless, but it is a triplet loss function. And this triplet loss function, again, I train it on the pre-trained BERT and the fine-tuned BERT. When I train on pre-trained BERT, loss comes out to usually about 0.52, and on the fine-tuned BERT comes out to 0.49. Now you're probably wondering, well, great, it's about a 0.03 difference. Why exactly does that matter? Well, it matters because of two things. First of all, when you're dealing with limited amounts of data, as much generalization and as much shaving off the losses you can get, the better. Second, I only trained this for 2 epochs, and we're already seeing a difference. And remember one more thing. My BERT, when it was fine-tuned, was only trained on line by line, whereas this next task that I'm training on downstream is trained section by section, so lines separated by separator tokens within BERT. And so keep in mind that my task isn't particularly ideal for pre-training, and yet I'm getting such a great performance boost. So with your domain-specific tasks, where you're actually pre-training on data that makes sense in your domain, you can only imagine the kinds of performance boosts you're going to get. And so this was a demo of why exactly it makes sense and how you can go ahead and sort of fine-tune BERT on your own data in a masked language modeling sense. All the code will be in the description, and hopefully that helped you realize what sort of training regimes you should be using for your neural networks. Of course, every task is different, going to require a completely different regime, but this gives you a pretty good idea of what direction to look in. I really do hope you enjoyed that tutorial. Once more, if you did, please do go ahead and subscribe to the channel. It really does help out a lot, and make sure to like the video as well if you did enjoy it. Now, of course, feel free to leave any questions down in the comments below. I'd love to go ahead and answer them, or as a GitHub issue on the repo in the link in the description. Apart from that, thank you very much, everyone, for joining in today. I really do appreciate it, and goodbye.